Hello students, welcome to my classroom advanced classes. So today we are going again after a week gap or 15 days gap, we are again starting these sessions. So earlier we have done some topics. So the today's topic is stoichiometry. So it is an important topic where we use in all physical chemistry applications or is even in any physical chemistry topics. Mostly we use this basic concept, and let us say in an advanced level the questions when coming. So let us see this topic, how we will solve in this advanced level or JEE advanced, how these questions can be answered. So this session might be helping you. So revising the stoichiometry topic. So let us start with that. Equivalent mass of HCl in the following reaction. So most of the applications are basically on the equivalent concept, let us say the mole concept, and let us say on limiting reagent based, percentage of the yield based. Maybe the application of mole concept we are doing, suppose in solutions, we see the concentration methods applications. In that we generally use this stoichiometric applications basically. So what is basically we say equivalent weight is? There are, let us say, like definitions in books what we see, it's the amount of substance that reacts with 8 grams of oxygen or 35.5 grams of chlorine or 108 grams of silver. In that fashion, in that terms we generally see the equivalent weight. But the basic definition of equivalent weight is, it's the amount of substance or the minimum amount of the substance that is required to take part in a chemical reaction. So for every reaction, there is a certain chemical reaction causing species. Suppose it is an acid base reaction. So H plus will be given by the acid, OH minus will be given by the base. So what is, if you say the acid and bases, what is the equivalent weights are? The amount of acid which gives a H plus ion, means if it gives a H plus, it immediately participates in the reaction. So a reaction causing species it has to produce. So for the acid it is 1 H plus, for the base it is 1 OH minus. Let us say if it is a redox reaction, we say electron loss and electron gain will be there in a redox reaction. So we say the number of electrons that are involved, based on that for 1 electron how much is required, that is our equivalent weight. So if you see this equation now, this equation is completely balanced, where we see the dichromate, potassium dichromate is undergoing reduction. So it is in the +6 state, it goes to +3 state. But in this HCl there is totally 14 HCl, some HCl is undergoing oxidation. So there are 6 chlorines which are actually changing from -1 to 0. So here there is a -1 state to 0 state it is coming. So the total number of electrons that are involved in the process, if you see, each chromium is +6, it converts to +3. So the total electron involved in this process is 6. Similarly, in the oxidation is also 6. So there are 6 electrons lost here, here there are 6 electrons gained. So what we say, totally 14 HCl molecules are consumed. So we should not take only the HCl which is involved in the redox, because total HCl that is in the process what we should actually always consider. Like let's say an example what we see, suppose you take a lead storage battery, we say H2SO4 actually does not involve in the reaction. But during that process, what is the equivalent weight of H2SO4 we say? So there will be 2 molecules of H2SO4 that has to consume in the lead storage batteries, while discharging or recharging it. So the 2 molecules will be involved and the 2 electrons are involved. So we say equivalent weight of H2SO4 in such cases, that is molecular weight by 1, that is molecular weight itself. So similarly, in this case where even HCl may not be, all 14 HCl are involved in the completely oxidation, but total molecules of HCl that is involved is 14. So what do we see? These 14 molecules are involved, but totally 6 electrons lost or gained. So the total electron involved in this process is 6. So what is equivalent weight is? Equivalent weight we generally use it as molecular weight by n factor. So what is n factor for this process is? That is electrons totally involved in oxidation or reduction here. So how many molecules are there? Totally 14. So it is for 14 molecules, that is molecular weight of HCl is 36.5 by total electron involved is in the process is 6. So this is an equivalent weight. So anyhow it cannot be 36.5, and most probably I think it is also not equal to 16.25. So it will come around say 73 or 85 maybe. But if you just see this is in terms of 7 and 3, so this is 10 times. So it should be around 85. Clear? Because it is coming around 12 point something. So it should be around 8 times. So it is 85. Clear? So let us move on to the next thing. So equivalent weight is always, it's the total number of molecules by total number of electrons involved. So what is generally you use an equivalent weight formula? So total number of molecules mass, that is what we say just as simply molecular mass by total number of electrons in the process, in the reaction. Okay? Coming to this. One mole of a mixture of N2 and NO2 and N2O4 has a mean molecular mass of 54.4. On heating to a temperature at which the N2O4 may be dissociated, let us say like completely mostly, into N2O4 is completely converting into 2NO2, like arrow is given, and even degree of dissociations or something is not mentioned. So assume that it is completely converted from N2O4 to NO2. Then the mean molecular tends to lower the value of 39.6. So the mean molecular mass becomes 39.6. It lowers the value of 39.6 it will show. What is the mole ratio of N2, NO2 and N2O4? So for this, let us say mean molecular mass when you are using for a mixture of compounds, mixture of let us say generally gases or something, components mainly, then what is mean molecular mass is? It's a simple relation that we just suppose take. What we say actually moles as? Moles is nothing but it's a mass by molecular mass or molecular weight, what we generally usually say. So the mixture when it is there, if we apply this thing, means this relation for completely to the mixture. But for the mixture, the mass, molecular mass, what we generally say as, it's a mixture molecular mass. Mixture molecular mass we generally say as mean molecular mass. So what is, you just apply this to mixture suppose, its number of moles of mixture then it is total mass of mixture by mean molecular mass of mixture or molecular mass of mixture, which is nothing but what we say is a mean molecular mass. So but usually now we don't know the masses also suppose, then we can convert like this. How to calculate mass? Then moles into molecular mass will always give mass of that compounds. So if you have, let us say, a mixer is 2 component system, then number of moles of first component is N1, its molecular weight is suppose M1, and second is suppose N2, then its molecular mass is suppose M2. So if it is a mixer of 2 components, or let us say use this is the 3 components, N2, NO2 and N2, mixer of 3 components. Then let us say N1, N2, N3 are moles, M1, M2, M3 are molecular weights, are molecular masses. Then what is mean molecular mass is? Mean molecular mass is, or mean molecular weight is, it is total mass that we multiply number of moles into molecular weights. So first component mass plus second component mass, third component mass. So I write N1 M1 plus N2 M2 plus N3 M3. This will give the component first component mass. This is giving the second component mass. This is giving the third component mass by total moles, that is N1 plus N2 plus N3. So here the total moles of that mixer is given as 1, but we don't know for N2 or NO2 and N2O4. But suppose if we assume one is suppose a variable, the second one is a variable, third one we just usually say total is 1, sum of these two, if you subtract from 1, you will get the moles of the other one. So let us say now number of moles of N2 is X, number of moles of NO2 is suppose Y, or let us usually say N2O4, this is given here, let us take this one as Y. This is Y. So the number of moles of this should become 1 minus X plus Y. So let us take the relation now. But already as we are saying N2O4 is converted into NO2, what will happen? So initial situation, the molecular mass is given as 55.4. After the dissociation, where N2O4 is completely converted into NO2, the mean molecular mass is becoming 39.6. Clear? So why the molecular mass is? The weight remains same, but the total number of moles will increase, because N2O4 is giving NO2, let us say 1 mole is giving 2 moles. So since the number of moles is increased, the mean molecular mass is decreased. So what we see, according to this relation what we use, and when we apply to the initial and final situations. So what is initial situation? At an initial situation, the mean molecular mass is 55.4, which is nothing but X into molecular mass of nitrogen 28 plus Y into, let us say, molecular mass of N2O4. So N2O4 is 28 plus 64. So 28 plus 64 is 92 plus the total number of moles of the NO2 is X, 1 minus X plus Y into, this is nothing but 46. This is the total mass of the mixer. By total moles is directly I can say 1. So let us say if this is an equation 1, taking out this 1, you just simply write now, this you just suppose remove simply, this we write it as simply 1, equation 1. Or you can expand this, and what is this after expansion, let us say, otherwise better we will do that, and we take that as an equation 1. So what is this 55.4? This is 28x, 92y, 46 minus 46x minus 46y. Clear? So this is 46y minus this 46 you can bring here, So if you subtract 46 from here, it is 0.4, 6 and that 5, 9 and 1. No, 1. Well, anyhow, 9.4. So this is 9.4. Means 46 plus 9.4 is 55. Then this is nothing but now 28x minus 46x. So this is nothing but 18x. So this is an equation 1. Now let us take after dissociation. So after dissociation, that is when N2O4 is completely converted into 2NO2. So we have Y moles of this. So initially these are already 1 minus X plus Y, that is already there. But after dissociation this will become 0. But this will become now 1 minus X plus Y plus 2Y. So what is overall this? The total moles of NO2 will be 1 minus X plus Y. This is minus Y, this is plus 2Y. So it is 1 minus X plus Y. But total moles of mixture, after dissociation is, so there is no N2O4. So there is only NO2 and N2. N2 is X plus NO2, that is 1 minus X plus Y. So that it becomes 1 plus Y. Clear? Now taking this and equating now to the second relation that is given, that is the second thing what is given. The mean molecular mass lowers the value of 39.6. So let us say write that one now. 39.6 lowers to a value, or what he gave, lowers to. So lowers to a value, is a different from lowers to a value. Lowers to a value means it is coming finally to 39.6. Lowers a value means you have to subtract from 55.42, or from 55.4 you have to decrease 39.6. So now it is anyhow lowers to 39.6. Total mass remains same, that is you can use the same relation. So that is I can say 46y minus 18x. This is the numerator term which was there. The total mass always remains same. So this is by 1 was there. So we are getting this relation. Clear? So sorry, this 46 plus 46 also should be, because this is 46, this is only this term. So in this 46 we have brought here, that's why, so the value, this part is all that what we are considering. By total number of moles, that is 1 plus 5. So expanding this is 39.6 plus 39.6y, this is 46y minus 18x plus 46. Here. So if you take all this term here, it is 18x, then this is 46 minus this 18x becoming plus, and 39.6 we are bringing here. So this is 46y minus 46, this becomes here and minus, so we are writing minus, so 46 39.6. So this is 0.4, this is 5, so 6, so 6.4y is equal to 46 minus 39.6, so 6.4 same. Okay. So this thing is an equation 2. So we got two relations here, two equations here. So equation 1 and an equation 2. So solving these two, so simple thing, that is now already what we have. So 1 plus 2 if I do, then this is minus 18x, this is plus 18x, this gets cancelled. then this is 46 and this is 6.4. So 6 if you remove, then it is 40 and you remove another 0.4. So it becomes 39.6. Y is equal to, this is 6.4 and this is 9.4 and 6.4. So it becomes nothing but 8 and this is 15.8. So you will get the Y value. So if we substitute Y value in any one of these equations, we get an X value. So then you can say what is the question, what was asked for us, what is the mole ratio of N2, NO2 and N2O4. So that we have to take as 1 minus X plus Y and Y. So get X and Y values, from that you can take the relation. I think clear? Okay. So we'll just go with the next now. So solve this Y value, then substitute in that, then get an X value, then you can get what is the relation or what is the ratio. Next, 1 gram of commercial silver nitrate is dissolved in 50 ml of water and it is treated with 50 ml of Ki solution. So we know that basic reaction of silver nitrate and Ki. So I think that is the reason why they have not mentioned this reaction, but the other reaction which is required for that problem he mentioned here. Then the silver iodide thus precipitated is filtered off. We removed that. Then excess of Ki which was there titrated with m/10 KiO3. So Ki and KiO3 reaction we have done. That is what we mentioned here in an acidic condition in presence of HCl, till all the iodide ions, that is I minus ions, are converted into ICl. So this is the thing what is important in this. All the iodide ions are converted into ICl. Now it requires 50 ml of m/10 KiO3 solution. But excess of Ki solution is titrated with m/10 KiO3 solution. Excess Ki whatever is left there. So for that we titrated with this, but how much of that KiO3 solution is consumed is 50 ml. If 20 ml of the same stock solution of Ki requires 30 ml of m/10 KiO3 solution, under the similar condition, what is the percentage of silver nitrate in the sample? So first what we see, we have taken 1 gram of a sample, but we don't know whether it is completely silver nitrate. It may be a silver nitrate. Then we say the percentage of silver nitrate in that sample will be 100%. We have taken 1 gram. In that 1 gram, suppose that total weight of the silver nitrate is 1, then I say it is completely silver nitrate. So it's a commercial sample, it may not be completely silver nitrate. We don't know, because we are asked to find out even percentage of silver nitrate there in that sample. So let us say there is some X grams. So we just calculate what is the weight of silver nitrate. So from the given data, we try to calculate the silver nitrate weight in it. Then what is the percentage of silver nitrate in that sample? In 1 gram, X grams is there. Then what is the percentage? So the weight of that component, pure weight of that component by total weight of that into 100 will give the percentages. So what we see, let us see the basic things. So silver nitrate is reacted with Ki, forms AgI, that will form a precipitate. Then we have a filtrate solution, that is KNO3. So the silver iodide is thus completely precipitated. Then if I suppose take excess of Ki solution titrated with this in presence of HCl, till all the iodide ions are completely converted into Ki. For that we require 50 ml of m/10. Means even if you take excess of this, if you take some m by 10.1 m concentration of Ki, we require 50. So as per the equation, which is already balanced here, what we say is 1 mole of this is reacting always with 2 moles of this. So how many moles of this we have taken? So let us say 50 ml is there, m by 10. So what we say, suppose millimoles of KiO3. What is millimoles of KiO3? 50 into this 0.1, that is nothing but 5. So how many millimoles of Ki has to react? Even we take excess. If we have taken 5, even in excess quantity it is there, it should be 10. Double. For 1 mole, 2 moles are required. For 5 millimoles, 10 millimoles are required. Clear? So this excess Ki solution that is titrated with m by E, then in presence of acid, that is nothing to do for us, that is not needed for us to take. Then required 50 ml of m by 10. So we dissolved in 50 ml. So 50 ml of Ki solution, and it is treated with 50 ml. So the total volume becomes 100. So what does this information say maybe is, there are 10 millimoles of Ki that is there in 100 ml. So what is concentration of Ki solution from here? The concentration of Ki solution is, and 20 ml of the same stock solution requires 20 ml of the same stock solution of Ki requires 30 ml of m by 10 KiO3 under the similar conditions. Okay. So you have to use this thing, I think, maybe, because you can calculate concentration of Ki from here itself, I think, because here we don't know excess of Ki solution, he said. So that we can't take. So let us use this now. 20 ml of the same stock solution requires 30 ml. So we have particular concentration of Ki, suppose particular concentration of Ki. What is that Ki concentration now? So if you take this relation, number of moles of KiO3 or millimoles of KiO3, what is number of millimoles of KiO3? That is 3. That is 30, otherwise you will write 30 into 1 by 10, that is 3. Then number of millimoles of Ki should be, how much of Ki should be there? Ki has to be, now this is 3, it should be double, so that is 6. But that we should get from 20 ml solution, which is of a particular concentration solution. So what is the concentration of that Ka solution which we used? So that is, number of millimoles of Ka is 6, that has to be equal to molarity into volume. So molarity we don't know, so volume is 20. So what is molarity is 6 by 20, or it is nothing but 3 by 10. So Ki solution concentration is 3 by 10. Clear? So might be this process is not anyhow required. Maybe here they wanted to do something, but this information anyhow was not that much useful for us. Now we know what is concentration of Ki. So we have some x grams of AgNO3 in that 1 gram, which we dissolved in 50, which is treated with 50 ml of Ki solution. Then silver iodide is precipitated and filtered off. Their intention is maybe if you just use this part, then let us see how much you are getting. Then maybe this excess may be something missing from here actually in the problem, that we will try to find out now. So let us see, there is a weight of silver nitrate in sample, if you say x grams, so that moles of silver nitrate will become x by molecular weight of silver nitrate 108 plus 14 plus 48. So 108, 14 plus 48, 27, 170. So it is x by 170. So let us see. Now we dissolve this in 50. Here, so we added 50 ml of Ki, which is of 3 by 10 concentration might be. So that if you use 50 ml of 3 by 10, how many moles of Ki should be there? Or what is Ki that is required? That completely reacts with silver nitrate. So whatever excess we added maybe. But anyhow, we got a Ki concentration here. Then there is, I think there is no need of this thing. Maybe if they are saying Ki is in excess, that Ki may be consuming this, then we say something. But otherwise, I don't think this has an importance here. Huh? So let us see. Number of moles of silver nitrate. So number of, let us say, millimoles. So millimoles of Ki, which is of a particular concentration Ki solution, 3 by 10. That is what we got is 3 by 10. Clear? So that 50 ml of Ki (50 into 3 by 10), so that it becomes 15 millimoles. But this is millimoles. So if you want to calculate in moles, so what is moles will be? If you want to say moles, what is moles will be? This is millimoles into or divided by 1000 will give moles. But silver nitrate and K react in 1:1. So x by 170 is equal to 15 by, that is moles of silver nitrate should be equal to moles of Ki. So 15 by 170, sorry, 15 by 1000. So what is x? So it is 170 into 15 by 1000. So this comes around more than 1, I think. 17, 15, 35, 5, 3, 5, 8, 7 and 1. So 5, 15, 1, 2. So you are getting actually it is around 2.55. So maybe this is the thing, let us see, because I don't see in this excess Ki, which was, means we added this 3 by 10 solution here, but some part of this only consumed, and how much of that was consumed is, so already we say suppose 50 ml of m by 10 is consumed, 10 is consumed. So how much we added is actually, what we got is 15. So 15 moles we added, in that 10 is consumed. So 5 reacted here. I think we'll write like this. So what we already say from here, just use this. We have KiO3 from this relation. We have 5 millimoles of KiO3. How many millimoles of Ki should react for this? 10. Totally how much we added? 15. So in this 15, how much was reacting only with silver nitrate maybe? How much was reacting with silver nitrate? Is only 5. So this is the total what we had. This is total what we had. So let us see. So that is the meaning of that, but wording was little bit not clear. So let us see. Total millimoles of this which we added is 15, this one, otherwise okay. Total moles. Total moles are moles, not total. Moles of Ki consumed for KiO3 is 10 by 1000. So what is this? So moles of Ki consumed for silver nitrate is 15 by 1000 what we added minus 10 by 1000. That is only consumed for Ki silver nitrate. That is 5 by 1000. So what should be weight of silver nitrate? That is X by 170 should be equal to 5 by 1000. So this is nothing but X is equal to 170 into 5 by 1000. So it is 85. So 0.85. Clear? So what is percentage of silver nitrate? Percentage of silver nitrate has to be now, there is only 0.85 grams in 1 gram. So that it is 85%. Clear? The excess Ki which was treated with KiO3. So he used the second information of KiO3 to calculate its concentration. Then total moles of KiO3 what we added was 15 by 1000. But the Ki which is consumed for KiO3 initially was 10 by 1000. So which was consumed only for silver nitrate was. That is subtraction, then you will get 5 by 1000. So now what we say this? Clear? So just see again once. There is 1 gram of a commercial sample of silver nitrate which we treated with the Ki solution. Then silver iodide was precipitated and that is removed. Then the excess Ki which was there in the solution, that was titrated with potassium iodide. KiO3 is called potassium iodide, M by 10. Then all the iodide will be converted into ICl, means whatever the Ki that is left, that is consumed here. So for that we require 50 of M by 10. So 5 millimoles are taken, then it will be 10 millimoles. Okay? So but if I use the same Ki solution there, 20 ml of the same Ki solution that is of this particular concentration, then 30 ml of M by 10 KiO3 is consumed under the similar conditions. So what is? So 10 millimoles are consumed here, but Ki what we calculate concentration as, if KiO3 is 3, then Ki should be 6. That you should get from molarity into volume of that. 20 ml of that is taken. So we are getting the molarity of Ki as 3 by 10. Clear? So then we calculated if a sample has X grams. Then let us see the next. A mixture of FeO and Fe3O4 when heated in air to a constant weight gain 5% in its weight. Find out the composition of the mixer. So this is what we see, the iron generally exists in two types of oxides. Iron usually exists in two types of basic oxides, that is Fe+2 and Fe+3. So what is Fe+2 oxide is? +2 oxide is nothing but what we say FeO, that is +3 oxide is nothing but formula is Fe2O3. So what we say, what is this Fe3O4 may be? That Fe3O4 may be, it's a mixture of these. So in what ratio they should be mixed? 1:1 type maybe. So then it is nothing but a mixture of FeO plus Fe2O3. Clear? But when we just try to react with air, what may happen? That FeO try to convert, means Fe+3 is more stable than Fe+2. Means iron oxide will try to completely convert into, any iron oxide try to completely convert into Fe2O3. Means iron oxide, this FeO changes to Fe2O3. Whatever the iron oxide that is FeO that is there in this Fe3O4 mixer, that also changes into Fe2O3. That is what we said, like a constant. What is given for us is a constant weight we are getting. So final weight will not change after that. Means there is no changes in the process that is happening. Means the iron is not undergoing any further changes in it. So we don't know that there is a mixer. So let us say when anything is not given for us. Now the way initially in the previous problem we had 1 gram of the sample is there. Now we don't know what is the weight of that mixer now. But we have to calculate what is their composition. Let us say percentage we are trying to calculate. Maybe ratio we are trying to calculate. Anything you can do maybe. If you get weights, you can take the ratio of weights, then you say percent, these are the things. Let us say mostly percentage is, or composition is nothing but we are saying in terms of let us say weights, percentages. So let us take total weight in such cases, because we have to calculate percentages. Total weight of mixer or initial mixer, let us say, is 100 or 100 grams. The initial weight of the mixer is, let us say, 100 grams, because we have to calculate composition, we have to say percentages. Then we usually take initially some fixed, and that fixed you better you take, because percentage we are trying to calculate, take it 100. You can take 1, you can take 2, you can take any quantity. But as for the given information, what is the final weight? Final weight of mixer. There is a 5% increase in it. What is mean by 5% increase is, it becomes 105. For 100, 5%. So the total weight finally becomes 105. But FeO reacts with oxygen and converts into Fe2O3. Clear? And similarly, Fe3O4 also reacts with oxygen and converts into Fe2O3. That iron Fe+2 converts into Fe2O3. Fe3O4 which may be taken as a mixture of FeO and Fe2O3, you say that is also converting. But I don't know how much ratio they exist. So let us use direct thing. These are the two components that exist. So let us say balancing this 2, then it becomes 2, but this is 2 plus 2, so it is half. Now this is 3, this is 2, so let us take this as 2, this as, that is 2, this is 3, this is 2, then iron gets balanced. This is 8, this is again only 9, so it is also half. So in this now, let us say if this weight is x, then the weight of this will become now nothing but 100 minus x. Okay. So what is, now we see what should be the weight of the total mixture is this. Clear? So what is actually adding is only oxygen is adding here. So I think you can take like this. For iron oxide, how much oxygen is required? Means for x grams, how much is required? For 100 minus x grams, how much is required? That weight if you add and equate to this, that will be the final weight. Because this iron oxide completely changes into Fe2O3. This Fe3O4 also completely changes into Fe2O3. So only which is adding here is oxygen. So what is the weight of oxygen that gets added? So iron atomic mass of iron is 56. So what is FeO? 56 plus 16. So that is 72. Okay. So here how much of iron is reacting? 2 means 2 times of that, what is that, is 72 grams reacts with 16 grams. So how much of oxygen will react here? That is 16x by this part. So how much of this will be here? What is Fe3O4? 56 into 3, 18. So 168. Okay. Then oxygen 64. So 12, 13, 2. So 2 into 232 grams is consuming 16 grams. So for this how much is required? So directly I write here what is the total weight of the mixture is 100 plus oxygen weight. So 100 plus what is the weight of oxygen for this process is, for 2 into 72 grams we require 16, half mole. So for x grams how much is required? That is 16x by 2 into 72 plus, for this now, for 2 into 232 grams we require 16 grams. So for 100 minus x how much is required? So 100 minus x into 16 by 2 into 232 will be equal to 105. Clear? So this is how we solve it, suppose. Then we will get the value of x. Then you can say what is the percentage of FeO. The remaining percentage will be Fe3O4. So you have to solve for x here. Calculation part, what is required, that you have to do it. Here. So that you do it, so that we can see the next question. So percentages you can calculate from here. Now, there is a solution of sodium carbonate and sodium bicarbonate. 20 ml of this solution requires 4 ml of 4 ml of 1 HCl for the titration with pH indicator. So it's phenolphthalein. It's phenolphthalein indicator. The titration was repeated with the same volume of the solution, but if we use this MEOH, so it is nothing but like methyl orange. Then 10 ml of same 1NHCl is consumed. Calculate the amount of sodium carbonate and sodium bicarbonate here. So when we use this applications of phenolphthalein, clear? So the titration was repeated with the same volume, means we started from the original. So there is double indicator titrations and all that. Means first we add an indicator like phenolphthalein, then we can start titrating with methyl orange also. Why? Because phenolphthalein can convert sodium carbonate into sodium bicarbonate, because there is a selection process of an indicators. Indicators always work in a particular range. So when we say suppose sodium carbonate whose pH is somewhere around 11, something like that, it's a not a stronger base also, somewhere 10 or 11 it will be there. So when we titrate with the, or when we neutralize it with the acid, its pH starts decreasing. When it reaches 8, then there is a permanent color change in the phenolphthalein indicator, where the indicator phenolphthalein, like indicator like phenolphthalein, is colorless in acidic condition and pink or orange, red color in basic condition. So it is sodium carbonate which is in basic nature. This is also basic, but when it reaches from this solution to this, or converted from here to here by neutralization of H plus, we say the pH of this solution becomes around 8 or 8.3, something like that. Then the color change is completely absurd. Means phenolphthalein completely becomes colorless. After that, when you even titrate the solution, means when you add acid, sodium bicarbonate gets neutralized. But where we have to stop the titration, we don't know. Means where we should end the titration, we don't know. So there is no meaning in doing or continuing the titration, because the indicator is basically used to know the equivalence or endpoints. So when already you are saying the solution becomes completely colorless, then there is no changes further addition of acid to the sodium bicarbonate here. So there you may do another indicator like methyl orange, we add, that we call it as a double indicator titration. Means you are adding, for titration you are adding 2 times. But suppose we use the concept of phenolphthalein and all this. So generally we take this in case of 3 general bases what we generally come across, that is sodium hydroxide, sodium carbonate and sodium bicarbonate. So when we just use the acid base titration or any titration, we just say any titration or a chemical reaction, usually we say number of equivalents of one substance will be equal to number of equivalents of the other substance. So now when we just try to use that equivalent concept, so when we have suppose sodium carbonate or sodium hydroxide and sodium bicarbonate, sodium hydroxide is completely neutralized first because it is a stronger base. So when we add acid, first sodium hydroxide gets neutralized. Then after that sodium carbonate, which is more basic than bicarbonate, that starts reacting with acids. Then sodium bicarbonate first converts into bicarbonate. Then from bicarbonate it changes into carbon dioxide, means this continues on addition of H plus and converts into H2O plus CO2 with suppose let us say sodium ions which exist with the acid conjugate base of that particular acid what we are adding. So the neutralization of sodium carbonate changes from bicarbonate to further. So when sodium carbonate you are saying it neutralizes in 2 stages, carbonate to bicarbonate, then bicarbonate to carbonic acid or carbon dioxide and water. Then bicarbonate is a single step again with an acid. So when we add suppose phenolphthalein indicator, what will happen? The pH changes will be seen and you will see only the pH when it becomes around 8, then the solution becomes completely colorless. Then there is no titration. So number of equimoles of acid or equivalents of acid always should be equal to number of equivalents of NaOH plus half of number of equivalents of Na2CO3, because only half of the equivalents we consume, because it is a 2 stages. So number of equivalents of acid will be equal to number of equivalents of NaOH plus number of equivalents of Na2CO3 by 2, because half of that is only neutralized. For complete neutralization we require, let us say, like 2. So when you add phenolphthalein later, suppose you add methyl orange later, what happens is already sodium hydroxide is completely neutralized. I will come to this problem later. So when already half of the Na2CO3 is neutralized, when you add methyl orange, sodium hydroxide was completely neutralized. Now the acid whatever we consume is only used for half of the equivalents of Na2CO3 whatever is there, and half of the total equivalents of sodium bicarbonate what is there. So number of equivalents of acid here should be equal to half of Na2CO3, we write simply like this, plus NaHCO3. I think get it? So it is sodium carbonate plus sodium bicarbonate. So when phenolphthalein is added, sodium hydroxide is neutralized completely, but bicarbonate is half is only completely consumed. Then when methyl orange is added to the same titration, so it's a 2 indicator titration. So for the neutralization of all the 3, mixture of those 3, we have to take 2 indicators. Clear? But if we add methyl orange directly, means for that direct mixture, NaOH plus Na2CO3 plus NaHCO3. If directly methyl orange is added, then equivalents of acid should be equal to equivalents of NaOH, Na2CO3 plus NaHCO3, because all gets consumed. Clear? Because all has to neutralize till that you don't see the color changes, because methyl orange around 3.5 to 5.5 range it works. So when it becomes around 3.5, the total all bases like sodium hydroxide, sodium carbonate, sodium bicarbonate, everything gets neutralized. Clear? So in this case what is he had done? First he used phenolphthalein, then he has taken again the same amount of mixer and he titrated again. So let us see using these basic applications, basic thing. So first, when phenolphthalein was used, equivalents of acid or HCl in this case should be equal to only half of equivalents of Na2CO3, because sodium hydroxide was not there. But later what he has done, he has not continued from here. He has taken the methyl orange there separately. Then the same volume of mixture was taken. So that number of equivalents of acid HCl now should be equal to Na2CO3 equivalents of Na2CO3 plus NaHCO3. Both will be neutralized at this stage. So let us see how many equivalents of HCl was used with the phenolphthalein case. 4 ml, 1 N or milli, whatever it is, milli or whatever it is, milli or 4 into 1 by 1000 is the number of equivalents of HCl. It is half of Na2CO3. This is equivalence of or equimoles of Na2CO3. What was the next thing? For methyl orange, 10.5 of same. So what is this thing? It is 10.5 into 1 by 1000, which is equal to Na2CO3 plus NaHCO3. So we can get what is Na2CO3 from here. Na2CO3 is nothing but from here, it's 8 by 1000. So it is 10.5 by 1000. This is 8 by 1000 plus NaHCO3. So number of equimoles of NaHCO3 will be nothing but 10.5 minus this part. So it is 2.5 by 1000. So number of equimoles of Na2CO3 is 8 by 1000. Clear? So that now what is the weight of Na2CO3? Weight of Na2CO3 will be equimoles into equivalent weight. What is equivalent weight of this is? This is n factories 2. So it is 8 by 1000 into 106 is the molecular weight of Na2CO3 by 2 is 53 is its equivalent weight. So the weight of Na2CO3 you will get from here. So what is weight of NaHCO3? So weight of NaHCO3 will be, this is 24 plus 60, 84. So equivalent weight of this is nothing but directly 84 only, molecular weight, because n factor of NaHCO3 is 1. It's a monobasic acid or monoacidic base, sorry, let us say, use that. Then this is diacidic base. I think clear? Clear? So that you will get the weight of NaHCO3 as well as Na2CO3 from here. So what he asked is, so the amount of these two. Is it clear? So how much is there in 20 ml? Okay. So number of milli equivalents in 20 ml, but anyhow, weight of directly we are calculating in 20 ml we are getting. The number of equivalents of these two in that 20 ml we are getting. Is it clear? Suppose it is asked for 1 liter. If it is asked for 1 liter, sometimes there are some questions which are asked for how much of Na2CO3, NaHCO3 that exists in 1 liter. So for 20 ml this much is there, for 1000. So you just take the proportion and then do that calculations. For 20 ml this many millimoles are there. For 1000 how much it will be there, or weight we calculated. From there you can say what is the weight in 20 grams is this much, in 1000 grams how much it will be. I think okay. Coming to the next. So use that calculation part, do the calculation part. Next. On heating KClO3 at a certain temperature, it is observed that 1 mole of KClO3 yields 1 mole of oxygen. What is the mole fraction of KClO4 in the final solid mixture containing only KCl and KClO4, the latter being formed by parallel reaction? So on heating KClO3, so when we see this thing KClO3 at a certain temperature, it is observed that 1 mole of KClO3 is giving 1 mole of O2. Means let us say KClO3 if it is heated, you will get mostly let us say like KCl and O2. Suppose you write like this, then this is suppose 2 moles, this is 2, then we will say this is 3. So 2 moles is giving 3 moles. Getting it? So that may not be the case in this situation maybe, because when we take like that, what is the given condition gets or will not satisfied. So, we have KCl O3 giving this. Maybe if you just use this thing, this is only just let us say KClO3 is giving KClO, then you will get. Okay. So KClO3 may be converted into KClO plus O2. So 1 mole is giving 1 mole of this and 1 mole of this. What is the mole fraction of KClO4 in the final solid mixture containing only KCl and KClO4 later being formed, later means KClO4 being formed in the parallel reactions. But as we see, KClO is an unstable compound, generally tries to convert into KCl plus into O, which simultaneously may oxidize KClO3 into KClO. So these might be the reactions that are involved in that as far as the information is concerned. So what is he is asking is, what is the mole fraction of KClO4 in the final solid mixture having these two. So while decomposing, it might be converting into this, then this is giving KCl plus O, then this O is oxidizing KClO3 simultaneously to KClO4. So finally what you may left, you will see only KClO3 is converting into KCl plus KClO4 plus O2, because this KClO cancels, O cancels. Clear? So final you may be getting this. So this is 2 moles. So now what is he is asking is, what is the final mixture? Means suppose you are starting with 2 moles of this. So KClO3 is suppose 2 moles. So then how much of this I should get? In that 1 mole is reacting, first you are giving 1 mole and 1 mole. Then in that 1 mole you are getting 1 mole of this and this nascent oxygen. Then this nascent oxygen is reacting with another 1 mole which is there. It is consuming, again giving 1 mole. So you will see 1 mole of this is consumed here, 1 mole of this is consumed here. So 2 moles is giving 1 mole of this, 1 mole of this and 1 mole of this overall. So what is the total KClO4 mole fraction? What is mole fraction? So mole fraction of KClO4 has to be. Finally we started with 2 moles. Initially we started with 2 moles of this, but we got 1 mole of this and 1 mole of this and 1 mole of this. So totally 3 moles exist. So that number of moles of this by total into 100. So it is our percentage we did. Now we just do this thing. Okay. So it is 1 by 3. Okay. So KClO4 is forming in the parallel reactions because of KClO which is giving, because we are writing this equation as per the given that like 1 mole of KClO3 is giving 1 mole of O2, then it might be a KClO plus O2. Okay. Otherwise general reaction is KCl plus O2. Next, what volume of 0.2 m KMnO4 solution is needed for the complete reaction with 26.56 grams of Fe.9O1 or FeO1 in the acidic medium. So what we usually say from this KMnO4 in acidic condition is manganese from +7 state it will change to +2 state. Hence KMnO4 is an oxidizing agent where it gets reduced. Then manganese oxidation state changes from +7 to +2 in acidic condition. So if you say MnO4 minus is converted into Mn+2, then this FeO or Fe.9O has to convert into like Fe2O3 or Fe+3. You can just use the simple thing, that is Fe+3. So here what is the iron oxidation state what we had is, what is the iron oxidation state we can say from this composition Fe.9O. So if you take this as generally X, this is -2, this is 0.9X, -2 is equal to 0. So X is equal to 2 by 0.9 or 20 by 9. Okay. So what is oxidation state of iron here is plus 20 by 9. So finally it changes to +3. So what is its N factor in this case? What is the N factor of Mn in this case is 5, or it has gained 5 electrons. What is the total in this case? So that we have 0.9. So oxidation state of iron changes from here to that. So it is +3 minus 20.9. So that it has to be now 927. So it is 7 by 9. So it is +7 by 9. So 7 by 9 electrons gained here, 5 electrons lost here. So how many moles of this has to react? 7 by 9 moles of this has to react, and 5 moles of this has to react. So what he is asking is, what is the volume of this? So what is moles of KMnO4 that is required is, so for 7 by 9 moles we require 5 moles. So let us say what is the weight of this, we try to find out first. So what is moles of Fe.9O? It is 26.56 grams by the mass of this. So what should be the mass of this is 56 into 0.9 plus 16. So it is 56 plus 0.9 into or plus 16. So let us see how much we will get. 56, 9, so 4, 5, 45, 50. So 50.4 plus 16. So 66.4. So it is 66.4. 66.4. Okay. So if this is 5, this is 7.9. So number of moles of this is 26.5. So for let us say 7 by 9 we require 5. For 26.56, 66 by 64 moles, how much of this is required? So cross multiplying. So 7 by 9 into 26.56 by 66.4 divided by 5. So this is the moles of KMnO4 that is required. So now concentration is there. So you can calculate what is the volume. So what is moles can be related from molarity things. Molarity, that is 0.2 into volume by 1000 should be equal to this 7 by 9 into 26.56, sorry, 56 is there, by 66.4 into 5. So this calculation parts. So approximately you can say maybe. Okay. Okay. Okay, next. So this is the volume in ml what you are getting. Okay, this is like just taking n factors. You can balance the n reaction or taking the moles relation by interchanging the n factors. So what is n factor of this is 5. What is n factor of this is from 20 by 9, it is converting into Fe plus 3. So iron will always change from general plus 2 to or iron there it is finally oxidized to Fe plus 3. Because KMnO4 itself will say even a stronger oxidizing agent also. Okay. So do the calculation things. A drug marijuana owes its activity to a tetrahydrocannabinol which contains 70% as many carbon atoms as hydrogen atoms, 15 times as many hydrogen atoms as oxygen atoms. So the number of moles in a gram of tetrahydrocannabinol is 0.00318. Determine the formula, molecular formula. So from this derivation, like 70% as many carbon atoms as that of hydrogen, 15 times hydrogen atoms as that of oxygen atoms. So there is saying from the information what we already know now is this compound has carbon, hydrogen and oxygen. So if you write carbon, hydrogen and oxygen. So what is, suppose we take a simple relation like 1, oxygen is suppose 1. How many hydrogen should be there? 15. Because 15 times hydrogen atoms are there as oxygens. So if oxygen is 1, hydrogen should become 15. Then carbon, 70% of hydrogens. Carbon atoms is 70% of hydrogen. So what is 70% of this 15? So into 0.7. So 15 sevenths. So it will be 35, 8.5. So you can take it as just like 8.5, no problem. So this is the formula what you can represent. Otherwise, if you want to write a simplest formula, this 8.5 is nothing but what we see as 17 by 2. So it will be C17 H30 O2 will be actually empirical formula. Okay. 70% of carbon atoms as hydrogens, 15 times hydrogen atoms as oxygens. So if you take oxygen as 1, hydrogen should become 15, then carbon should become 70% of that 15, 80.5. Clear? So then, not sorry, 1 minute. This is 10.5, sorry, not 8.5. 1535, no? 8.5, not this. So it is 10.5 or 21 by 2. So 21, 30. So what is he saying is number of moles in 1 gram. So moles of that component is given as 0.00318 in 1 gram. So 1 by molecular mass is 0.00318. So what is molecular mass is? Molecular mass of this will be 1 by 0.00318. So what is molecular formula? So we already usually say molecular formula may be some n times of its empirical formula. So what is empirical formula weight? Empirical formula weight is 21 into 12. So 12, 21 to 1 4, 2, 2, 5, 2 plus 30 plus 32. So 4, this is 6, 1, 3, 314. Clear? So what is empirical formula or molecular formula? Sorry. Molecular formula will be, this is molecular mass by that will give empirical number of like times. So it is n number or empirical molecular formula we write as empirical formula by n times. N is molecular formula weight. So it may be, now as you just see from this, it might be this itself. Looks like that only. So it is 16, this is not 50, this is somewhere 30 and 15, this is 15 and 17. So this is the only relation that satisfies. Okay. So this is nothing but you may get now 340. So that empirical formula and molecular formula are same. N is equal to 1. Because anyhow you are seeing the carbon is not 70% of hydrogens. This carbon is not 70% of hydrogens. Clear? So this is the only formula which satisfies. An amount of 5 moles of A, 6 moles of B and excess of C are mixed to produce the final product D according to the following reactions. So I is some like intermediate product you are getting maybe. So I is an intermediate product which is obtained from A and B. Then I plus C is reacting to give B and D. So your final product is you are getting again as a D. Suppose what is the maximum moles of D which can be produced assuming that the products formed can also be reused in the reactions. So as you see, A plus 2B is giving first I. So how many moles of this is there? 5. How many moles of this is there? 6. So this is initially anyhow 0. But 1 will react with 2. So 5 moles should react with actually 10 moles. So we say the B is only 6. We need 10 moles to react or completely consume this 5. So that we say B is not in sufficient quantity. So B we say like limiting reagent for this. So B has to consume completely first. So B consumes completely, but for 2 moles, 1 mole has to consume. So for 5 moles, 3 moles only gets consumed. Half of that gets consumed. So 5 minus 3, that is 2 moles of A will be left like that. Then if 6 moles of this is reacting, you will get 1 mole of this. 2 moles, you will get 1 mole of this. For 6 moles, you will get 3 moles of this. But we have an excess amount of C. Okay. So I is reacting with C to give B plus D. But how many maximum moles we will get? But a product which is suppose forming, or let us say B is forming in the second equation, that B may also again react with left out A. That is the meaning actually what is asking maximum that can be reused again. So we got 3 moles of this. We have excess of this. Anyhow. So this 3 has to completely consume. So you will get first 3 and 3. Clear? Now we got again 3 moles of this and 2 moles of this is left. So now for this 2 moles, how much of this is required? again 4, but we have again only 3. So this 3 consumes 0. So how much of this reacts? 3 by 2, 1.5. So 2 minus 1.5. So 0.5 of A will be left now again. Then already we got 3 moles of this is consumed. I will get again 3 moles of this. That is in the second stage you are getting 3 moles. That 3 moles again will react here. That 3 gets consumed again with excess is anyhow there. You will get again 3 moles of this and 3 moles of this. So this will become 3 plus 3 already, 6. Now we got again 3 moles of this. B we got 3 again. So for A plus 2B is giving I. We got again 3 moles of this. 0.5 moles of this was there. Then what should happen? Here for 3 moles, you don't have a sufficient 1.5. So now this A becomes limiting. So A completely consumes again. So for A, how much of this has to react? Double. So 1 has to react. 2 moles of this will be left. Then how much of this you will get? For 1 you will get 1.5. So 0.5 moles of this again reacts. Again excess is there anyhow. You will get again 0.5 of this and 0.5 of this. So overall amount of D formed is, what is there missing? 6, you will get 3. For 3, sorry, this is wrong what we have taken. This is not 3. This is nothing but what we say. For 2 we will get 1. So for here 3 you will get 1.5 only. So this part is 1.5. So this is 1.5. This is 1.5. This is 1.5. So 1.5 plus 3 plus 0.5. So it will be nothing but 5. Okay? Clear? Now coming to the next. Molecular masses of NH3 and N2 are X1 and X2 in the reaction. That equivalent weight of are Y1 and Y2. Then Y1 minus Y2. What is already we said what is N factor here. So for nitrogen, if molecular mass is X2, NH3, that this N2, what is total number of electron involved for the nitrogen and hydrogen here? Nitrogen, which was 0 oxidation state here, it changes to -3 here. So there are 2 nitrogens, they are changing to -3, it is 6 electrons gain. So hydrogen, which is in 0, it is converting into +6, sorry, +1. So here the N factor is nothing but 6. So here it is a 6 electron loss, here it is a, sorry, it is a 6 electron loss, it's a 6 electron gain. So N factor for nitrogen will be, N factor for nitrogen, it is only 1 mole is there and 6 electrons are involved. So N factor for nitrogen is 6. And what is N factor for, suppose we are only using the NH3 and N2 in this, their equivalent weights are Y1 and Y2. So what is NH3 equivalent mass is? N factor is. N factor of NH3 for 2 moles 6 electrons are involved in the reverse process. So what is N factor of NH3 is 3. So what is equivalent weight or equivalent mass of nitrogen is, equivalent mass of nitrogen is Y2, and in the respective terms if you take, it is Y2. Y2 should be equal to molecular mass of N2, that is X2, by N factor of N2. So this is N factor for nitrogen, this is N factor for NH3. So that is nothing but 6. So x2 or anyhow, we have to take y1 minus y2. So let us use y terms only. What is equivalent mass of NH3? Equivalent mass of NH3 is nothing but y1, which is nothing but x1 by 3. Clear? So what is he is asking, what is y1 minus y2? So what is y1 minus y2? Is x1 by 3 minus x2 by 6. So it will be 6 2x1 minus x2. Okay. Okay. So this is the thing. So this is the general way, like basic stoichiometric mole relations, equivalent relations, applications, and let us meet in the next session and with the next topic. Okay. Thank you.